In the previous video, we used the graphing method to solve a system of equations involving a linear function and a quadratic function. In this video, we are going to use the substitution method. We will use the same method that you used in grade 10 when solving linear systems using the substitution method. These steps are as follows. Step 1, label both equations as equation 1 and 2. Step 2, if necessary, isolate either x or y from one of the equations and label this equation 3. Usually we isolate for y because it's easier. Step 3, sub one equation into another equation. Step 4, solve for either x or y. Step 5, sub the value that you solved for in step 4 into one of the other equations and solve for the other variable. Step 6, state the solution in coordinate form x, y. This is your point of intersection. And step 7, check if asked by substituting the coordinate x, y into the left side and right side of both of the original equations. When solving linear systems in grade 10, there was only ever one point of intersection, if any. So that would have given you one x value and one y value. When solving a system involving a linear function and a quadratic function, as we're going to do in this example, you could get up to 2 solutions. So you may find 2 x values or 2 y values in step 4. In this first example, I am given a linear equation, y equals 6x minus 1, and a quadratic equation, y equals x squared plus 4, and I want to solve the system. I've already labeled equation 1 and equation 2. Both equations have the variable y isolated, so I do not need to rearrange either equation. So I can complete step 3, which says sub one equation into the other equation. So I'm going to substitute 6x minus 1 from the first equation where y is in the second equation. And I get an equation 6x minus 1 equals x squared plus 4. This is a quadratic equation that I need to solve because of this x squared. When solving a quadratic equation, you always need to make the equation equal to 0. So what I'm going to do is bring these two terms on the left side to the same side as the x squared plus 4. So I'm going to subtract 6x from both sides and add 1 to both sides. So when I do that, I get x squared minus 6x plus 5. And on the left side, I get a value of 0. Again, you must ensure that you write this 0 on one side before factoring and solving this quadratic equation. So now to solve, I'm going to try to first factor, and then if not, I'll use the quadratic formula to solve this quadratic equation. I see that this is a simple trinomial, so I want to find two numbers that multiply to 5 and add to -6. And I get x minus 1 and x minus 5 works. Take each bracket and solve. So I'm going to have 2 points of intersection, one when the x value is 5 and the other when the x value is 1. So now my next step is to find the corresponding y values for each of these x values, and I'm going to do that by substituting in 1 and then 5 into either equation 1 from the beginning or equation 2. Usually it's going to be easier to substitute into your linear function, so I will use that. You will get the same for either function that you put in if your x values are correct. So y equals 6 times 1 minus 1, so y equals 5. Therefore, my first point of intersection is 1, 5. And then I'm going to do the same thing for when x is 5. I'm going to substitute it into the same equation. So this time 6 times 5 minus 1, which is 29. So therefore, my second point of intersection is 5, 29. And the last step that you could be asked to do is to check your solution. This is just also a good thing to do, just to see the accuracy of your answers, even if you're not asked to do it. So what I'm going to do first is my first point, which was 1, 5. I'm going to substitute it into the left side and the right side of my linear function. So my left side was y, so my y value from this solution is 5. And my right side was 1, so I'll substitute that. 6 times 1 minus 1 is 5. So because 5 equals 5, I know my solution satisfies the linear function. And then I'm going to check it also into my quadratic function. So y equals x squared plus 4. So again, I'll substitute in 5 for y, 1 for x. And I get 5 is equal to 5 again. So this solution, 1, 5, satisfies both the linear function and the quadratic function. So I'm pretty confident about my answer. Next, I'm going to take my second solution and do the exact same thing. I'm going to substitute it into my linear function and my quadratic function to make sure that the left side equals the right side. So here I have my left side is y, so here y is 29. My right side, 6 times 5 take away 1, which is 29. So my left side equals my right side. And then in equation 2, my left side is 29, my y value, and my right side is 5 squared plus 4, which is equal to 29 as well. So both my solutions look correct, and you can also check by using Desmos to see if that is where the line meets the parabola. I will now do another example using the substitution method. I recommend that everybody watches this example as well as the first example, because this one has a little bit of a different solution. So here again I have the two equations, so I'm going to label them equation 1 and equation 2. Both equations have y isolated, so I don't need to do any rearranging. And now I'm going to take the 3x minus 1 and substitute it in where my y term is on my second equation. And I get 3x plus 1 equals negative 2x squared plus 16x minus 31. Anytime I solve a quadratic, I prefer to have my x squared term as positive, and since I need to rearrange terms anyway, I'm going to rearrange all three of these terms on my right hand side and move them to my left side of my equation. So I'm going to add 2x squared on both sides, take away 16x on both sides, and add 31 on both sides. So my simplified equation becomes 2x squared minus 13x plus 32 equals 0. Again, I want to highlight that we equal to 0 before we start solving. So first I'm going to look to see if I can factor this equation. So I have a coefficient of 2 in front of the x squared, so I'd like to common factor that if I can, but I can't. I can take it out of 32, but I can't take it out of 13. So then I'm going to try to use decomposition, as this is a complex trinomial. So I want two numbers that multiply to 64 and add to negative 13. So once you play with that for a little bit, you realize that you cannot find two numbers that will work, so you cannot factor. So then to try to solve, what you would have to use is a quadratic formula, which you should have memorized by now. And then you substitute in, your b value is 13. Your a value is 2, and your c value is 32. So then you continue to simplify in the quadratic formula, and you get 13 plus or minus 169 minus 256 divided by 4. So inside the square root, you actually get a negative 143, which we know is not possible to square root, meaning that this quadratic equation does not have any solutions. So in context of this problem, this means that the parabola and the line will not intersect. So it would look something like this, where you can see that the line and the parabola will not meet. Therefore, it's impossible to solve for solutions because there are none. Anytime I get that there are no solutions, I always just double check my work to make sure that I should have had negative underneath the square root. And on assessments, the question will always say, find the solutions where possible, meaning that sometimes it is not possible that the system will have a solution. So what you would need to do is show that somehow. And we did. We showed our work here. We tried to find a solution. We found that there's negative underneath the square root, which means there are no solutions because it can't be solved. So then we can just say, therefore, there are no solutions. So we showed enough of our steps and we've interpreted our work to get full marks on this problem. Before we leave this question, I just want to go back up to where we figured out that we could not factor that quadratic equation, so we started the quadratic formula. Something that would have been smart to have done before we use the quadratic formula is just check with the discriminant to see if it is even worth taking our time to try to use the quadratic formula to find solutions, which in this case it wasn't. So our discriminant is b squared minus 4ac, so negative 13 squared minus 4 times 2 times 32, which is equal to negative 143, which we already knew because that's what we got in the square root of the quadratic formula. So because the discriminant is negative, we can say, therefore, there are no solutions. And we don't need to actually go and try to find them because we already showed using the discriminant that there are none to find. If we found that the discriminant was equal to 0, we would have known that there would have been one solution to have found. And if it was greater than 0, we would have known that there would have been two solutions. So then we would have had to go and use a quadratic formula to have found those two solutions.